field due to electric current.
Good morning, student. Now we want to see the second case for to obtain the equation of force acting on the wire which carries the current. Right? In previous one, we have already seen that the force acting on a straight conductor. Now we want to see the force acting on a arbitrary shape of the conductor. But before that, we know that the equation of the force acting on a straight conductor. For straight conductor, equation of force is what is it there? F, which is equal to the I into the L cross B. Right? Now suppose this will be the equation of the force for the straight conductor. Now we want to see the second case for the arbitrary shape of the conductor. Arbitrary shape of conductor. It means that here we want to take the one of the arbitrary shape of the conductor. Suppose this will be the one of the arbitrary shape of the conductor. Right? And here, suppose that if we consider here the one of the magnetic field is present. Again, the direction of magnetic field is perpendicular to the plane of the figure, and again which is their direction is in outward direction. Right? Here we want to take the first of all small element of this conductor. And we know that the direction of flow of current is, it means that along this direction the current is flow. Right? Now we want to take the infinitesimal length of the conductor. Suppose if you consider this will be the length is dl. Right? Then this magnetic field which acts the force on this element. Then the value of that force is from the last equation. What is there? Here the equation of the force is dF. Here we take the dF because of here we consider the small part of the whole conductor. For whole conductor force is this one. But for the small element the value of force is dF, which is equal to the. Here current is as it is, that is I. But here, instead of L, we want to take the small dl. So what is it there? dl cross, what is it there? B. Here B is the magnitude of magnetic field. Simply B represents the magnitude of magnetic field. But here, vector B represents the magnetic induction. Right? Now this is about the only small element. But for the whole conductor, what is it there? For whole conductor. For whole conductor, this equation which is written as simply F, which is equal to the integration of simply dF. Right? It means that this will be the value, this will be the formula for the small element, now for the whole conductor. So here we want to take the summation or integration. Here we take the integration, that is the integration of df. But the value of df is this one. So put that value, so what is it there? So this r is as it is. Right? So what is it there? Integration of vector dl cross vector b. But suppose here if we consider the value of b is remain same. That is, here the magnetic field is present, but that magnetic field is the uniform magnetic field. Then this equation which is written as vector F, which is equal to the I. So the inside the bracket integration of simply vector dl here cross vector v. Right? Now this will be the equation of force for the arbitrary shape of the conductor. Right? See all the equations once. See. Now, we want to find out the third part. That is, force on a closed circuit inside the magnetic field, or magnetic force on a closed circuit. But we know the last equation. Which one? We know that the magnetic force on a arbitrary shape of the conductor, what we get there? Fm, which is equal to the, what we get there? This R is as it is. Then integration, right? Integration of vector dl cross vector v. Now this is the equation for the arbitrary shape of the conductor. Now we want to find out the same equation for a closed circuit. For closed circuit. Here we write the same equation. That's like here Fm, which is equal to this R is as it is. Then integration over the closed loop or closed surface. Right? So what we get there? Vector dl. This one is as it is, so this will be the vector v. For the closed circuit, we write here Fn, which is equal to the I into the integration for the closed loop or closed circuit. That is V. Right? dl cross v. Again here the length vector for a closed circuit is here the value of integration for the closed surface, so dl which is equal to the 0. Right? Then this equation which is written as Fm which is equal to the 0. Here V is uniform. V is uniform or V which is not equal to the 0. Here the value of V which is not equal to 0, then and there here the force acting on that closed loop or closed circuit is 0 because of the value of this length vector for the closed loop is or closed circuit is 0. So that's why the force acting on that closed loop is 0. Right? See all the equations. Cross B. Suppose here if you write this equation in terms of the magnitude, so what we get there? Fm which is equal to the Q into the V into the B into the sine theta. Here sine theta due to the cross product. In cross product we take the sine theta. Suppose here the angle between the V and B is 90. If theta which is equal to the 90 degree. It means that angle between the velocity of the charged particle and magnetic field is 90 degree. Then what we get there? Then sine 90 which is equal to the, what we get there? Sine 90 which is equal to the 1. So what we get there? So force Fm which is equal to the QVB. Now rearranging this one. So B which is equal to the, what we get there? Magnetic force upon charge into the velocity. Right? Now we want to find out the SI unit of the magnetic field. Here, first of here, this will be the force. Any force which is measured in Newton. Right? Then charge. Charge is measured in Coulomb. And V is the velocity which is measured in meter per second. Then, now here we want to write down this equation again. What we get there? Newton. Now this is the second at denominator of the denominator, so transfer to numerator. So what we get there? Newton second per coulomb meter. Right? Now this will be the SI unit of the magnetic field or magnetic induction. What we get there? Newton second per coulomb meter. Again here, this magnetic field which is measured in Tesla. Which one? Tesla. And the value of 1 Tesla which is equal to the 10 raised to 4 Gauss. Here, Gauss is not the SI unit of this magnetic field. But for our convenience, we take the Gauss. Gauss is the name of the scientist. So that's why 1 Tesla which is equal to the 10 raised to 4 Gauss. So what we get there? Once we want to write down 1 Tesla which is equal to the 10 raised to 4 Gauss which is equal to the, what we get there? 1 Newton second per coulomb meter. So this will be the SI unit of the magnetic induction. Now see once.